For 4.5 billion years, it has drifted through the cosmic dark, a lonely blue marble, forging life from stardust and fire. We walk its surface, we build our cities, and we map its borders. We believe we know our home, but the ground beneath our feet is not silent. It is a library of time, where every layer of rock, every drop of water, and every grain of sand holds a memory. From the violent furnace of the core to the silent whispers of the deep oceans, there are chapters of history we have yet to read. It is time to peel back the layers of time. Welcome to the hidden stories of our ancient home, Earth's deepest secrets. Let me take you on a gentle journey through time and space, where we'll explore the most extraordinary secrets of our planet Earth. As you settle in, relax, and let these stories wash over you like waves upon an ancient shore, know that each fact we explore together is a window into the magnificent complexity of the world beneath your feet and above your head. The Great Silence. Beneath Antarctica, we begin our journey in perhaps the most unexpected place on Earth, deep beneath the frozen continent of Antarctica, where something truly remarkable exists that contradicts everything most people assume about this icy realm. Imagine, if you will, descending through miles of ancient ice, past layers that hold trapped air from times when our ancestors were just beginning to walk upright, past frozen meteors and volcanic ash from eruptions that predated human civilization entirely. There, in the absolute darkness, beneath pressures that would crush almost any living thing, you would discover something that challenges our very understanding of where life can exist. Lake Vostok, hidden beneath more than 2 miles of solid ice, is one of Earth's largest lakes, containing more than 1,200 cubic miles of liquid water. This water has been sealed away from our atmosphere for perhaps 15 to 20 million years, existing in complete isolation from the surface world. The weight of the ice above creates immense pressure, which, combined with geothermal heat from Earth's interior, keeps the water liquid despite temperatures that would otherwise freeze it solid. Scientists have discovered that this ancient lake contains life, microorganisms that have evolved in total darkness, in isolation so complete that they represent an entirely separate experiment in evolution, one that has been running for millions of years without any contact with the outside world. The water in Lake Vostok is incredibly pure, so pure that it's almost like distilled water, yet it contains dissolved oxygen at levels 50 times higher than typical surface lakes. This oxygen comes not from photosynthesis, as it would in a normal lake, but from the slow melting of ancient ice crystals that trap air bubbles from Earth's distant past. The organisms living in these waters have adapted to survive on this oxygen and on minerals dissolved from the rocks below. They exist in perpetual darkness, in cold that hovers just above freezing, under crushing pressure, yet they thrive. Some scientists believe that studying these organisms could help us understand how life might exist on other worlds, particularly on Jupiter's moon Europa or Saturn's moon Enceladus, both of which have vast oceans hidden beneath frozen surfaces. The discovery of Lake Vostok and the realization that it harbors life fundamentally changed our understanding of the limits of biology. For millions upon millions of years, while dinosaurs rose and fell, while continents drifted and reformed, while our own species emerged and spread across the planet, these microorganisms were living their quiet existence in the dark, adapting and evolving in ways we are only beginning to understand. The lake itself is larger than Lake Ontario, stretching over 150 miles in length and 30 miles at its widest point, making it one of the world's largest lakes despite being completely hidden from view. What makes this even more fascinating is that Lake Vostok is not alone. Scientists have now identified more than 400 similar lakes beneath the Antarctic ice sheet, creating an entire hidden aquatic landscape that exists in perpetual night. Some of these lakes are connected by rivers that flow beneath the ice, creating a network of waterways that have been operating independently of Earth's surface systems for incomprehensible spans of time. Each lake potentially harbors its own unique ecosystem, adapted to its particular conditions of depth, pressure, temperature, and mineral content. The ice above these lakes tells its own story. When scientists drill ice cores from above Lake Vostok, they're extracting a record of Earth's climate going back hundreds of thousands of years. Each layer of ice contains trapped bubbles of ancient atmosphere, volcanic ash from eruptions long forgotten, cosmic dust from space, and chemical signatures of past climates. Reading these cores is like reading the pages of Earth's autobiography, written in ice instead of ink. The deepest cores reveal times when the Antarctic was actually green and temperate, when forests grew where now only ice exists, reminding us that our planet is always changing, always transforming, operating on timescales that dwarf human experience. The breathing planet. As you continue to relax into this journey, let's move from the frozen south to consider something that happens on a global scale. Something so vast that it's visible from space, yet so subtle that most people never notice it at all. Our Earth breathes, not metaphorically, but in a quite literal sense that becomes apparent when you observe our planet over the course of seasons. From space, satellites have measured something remarkable. Earth actually grows larger and smaller with the changing seasons. The planet's atmosphere expands and contracts in a gentle rhythm that mirrors the growth and dormancy of plant life across the continents. During the Northern Hemisphere summer, when vast forests across North America, Europe, and Asia are in full leaf, photosynthesis draws enormous amounts of carbon dioxide from the atmosphere. These forests, grasslands, and other ecosystems absorb this carbon dioxide and release oxygen, effectively cleaning and refreshing the air. This process is so massive in scale that it causes a measurable change in atmospheric composition and even in the planet's gravitational field, though the gravitational changes are extremely subtle. When autumn arrives and leaves begin to fall, when plants enter dormancy and begin to decay, this process reverses. The carbon stored in plant matter is released back into the atmosphere as decomposition occurs. The atmosphere becomes slightly enriched with carbon dioxide, and the planet, in a sense, exhales. This annual breath cycle is so pronounced that scientists can track it by measuring atmospheric carbon dioxide levels at monitoring stations around the world. The measurements show a regular annual oscillation, like a heartbeat or a breath, rising and falling with the seasons. But there's more to this breathing than just atmospheric composition. The biosphere itself expands and contracts with the seasons. During summer in the Northern Hemisphere, where most of Earth's landmass is concentrated, the total amount of green plant matter on the planet reaches its maximum. Forests are thick with leaves, grasslands are lush, crops are growing. The sheer mass of this vegetation is significant enough that it actually affects Earth's overall density distribution, though to a degree so small that only sophisticated instruments can detect it. When winter comes and leaves fall, when grasslands brown and crops are harvested, the planet's living green biomass decreases substantially. This seasonal breathing extends to the oceans as well, though in a more complex way. Ocean phytoplankton, tiny photosynthetic organisms that drift in the surface waters, bloom in tremendous numbers when conditions are right, when nutrients are available and sunlight is abundant. These blooms can be vast enough to change the color of the ocean when viewed from space, turning blue waters to green or brown with the dense concentration of microscopic life. These phytoplankton are performing photosynthesis just like land plants, drawing down carbon dioxide and producing oxygen. In fact, it's estimated that ocean phytoplankton produce at least half, and possibly as much as 80% of Earth's oxygen. Every other breath you take comes from these microscopic organisms drifting in the sea, organisms so small that millions of them could fit in a teaspoon of seawater. The seasonal phytoplankton blooms follow complex patterns driven by ocean currents, nutrient upwelling, temperature changes, and light availability. In the North Atlantic, spring brings massive blooms that can cover areas larger than entire countries. These blooms support entire food webs, from tiny zooplankton to vast schools of fish, to the great whales that migrate thousands of miles to feed in these productive waters. When the blooms fade and the plankton die, they sink toward the ocean floor, carrying with them the carbon they absorbed during photosynthesis, effectively removing it from the atmosphere and storing it in the deep ocean or in seafloor sediments. This grand planetary breathing is intimately connected with Earth's climate systems. The carbon dioxide that plants absorb during their growing season is temporarily removed from the atmosphere, while the carbon released during decay periods returns to the air. On geological timescales, some of this carbon becomes locked away in soils, in peat bogs, in ocean sediments, and eventually in rocks, creating a long-term carbon storage system that has helped regulate Earth's climate for hundreds of millions of years. The coal, oil, and natural gas we burn today are actually the remains of ancient plants and plankton that lived hundreds of millions of years ago, organisms that breathed in carbon dioxide during their lives, and then were buried before they could fully decay, locking away their carbon for eons. Understanding Earth's breathing helps us appreciate the intimate connection between the living and non-living parts of our planet. The atmosphere, the oceans, the rocks, and the biosphere are not separate systems, but deeply interwoven parts of a single planetary whole. The air you breathe has been cycled through countless organisms over billions of years. The oxygen molecules entering your lungs might have been produced by a fern in a carboniferous forest 300 million years ago, or by a microscopic ocean organism last week, or by a tree in the Amazon rainforest yesterday. You are breathing the exhalations of life itself, participating in a planetary exchange that connects you to every photosynthetic organism that has ever lived. The ancient ocean in the sky. Let us now drift from Earth's breathing to another mystery that surrounds our planet every moment: the origin and nature of our oceans, specifically the water vapor that fills our atmosphere. Most people know that water evaporates from the oceans and returns as rain, but the full story of Earth's water is far stranger and more ancient than this simple cycle suggests. The water in Earth's oceans, and indeed all the water on our planet, is almost as old as the solar system itself. Some of it, perhaps most of it, came from comets and asteroids that bombarded the early Earth during the first few 100 million years after our planet formed. These ancient impacts delivered not just water, but also organic molecules, the chemical building blocks that would eventually give rise to life. The water molecules in the glass you drink from today have been part of Earth for more than 4 billion years, cycling endlessly through oceans, atmosphere, ice, living organisms, and rocks. What's particularly remarkable is that Earth holds its water in a delicate balance. Our planet is positioned in what astronomers call the habitable zone, at just the right distance from the sun, where temperatures allow water to exist in all three states: solid ice, liquid water, and water vapor. Venus, our closest planetary neighbor toward the sun, lost its water long ago to a runaway greenhouse effect that boiled its oceans away into space. Mars, farther from the sun, lost most of its water when its magnetic field failed, and solar winds stripped away much of its atmosphere. Earth, blessed with the right size, the right distance from the sun, and a protective magnetic field generated by its rotating liquid metal core, has managed to hold onto its water through billions of years. The amount of water in Earth's atmosphere at any given moment is relatively small, enough to cover the entire planet to a depth of about 1 inch, if it all fell at once. Yet this atmospheric water is constantly moving and cycling at an extraordinary rate. On average, a water molecule spends about 9 days in the atmosphere before falling as precipitation. This means that the entire atmospheric inventory of water is replaced roughly 40 times per year. Some water molecules may spend years frozen in polar ice or decades slowly flowing through groundwater systems, but atmospheric water is in constant rapid motion. The patterns of this motion create Earth's weather and climate. Water vapor is the most important greenhouse gas, more significant than carbon dioxide in terms of its immediate warming effect on our planet. When water evaporates from the ocean surface, it carries with it tremendous amounts of energy, the latent heat of vaporization, which is released when the vapor condenses back into liquid droplets to form clouds. This energy transfer drives atmospheric circulation, powering winds, storms, and the great circulation patterns that move heat from the equator toward the poles. The clouds that form when water vapor condenses play multiple roles in Earth's climate system. Low, thick clouds tend to cool the planet by reflecting sunlight back to space before it can warm the surface. High, thin clouds tend to warm the planet by allowing sunlight to pass through, but trapping infrared heat trying to escape back to space. The balance between these effects and how clouds might change as the climate changes remains one of the most important questions in climate science. Understanding clouds requires understanding not just water vapor, but also the tiny particles, called aerosols, that water vapor condenses upon. These aerosols can be sea salt spray, dust, volcanic emissions, or even particles produced by living organisms. Without these condensation nuclei, clouds would be far less likely to form, and Earth's climate would be dramatically different. Deep beneath the surface, Earth holds even more water than floats in the atmosphere. Groundwater fills pores and cracks in rocks, sometimes forming vast underground aquifers that hold more fresh water than all of Earth's rivers and lakes combined. Some of this groundwater is very old, having fallen as rain thousands or even millions of years ago, and slowly percolated down through soil and rock. In some places, drilling wells brings up fossil water that fell during the last ice age, water that last saw the surface when mammoths walked the earth. But there's even more water hidden deeper still, locked within the crystal structures of minerals in Earth's mantle. At the high pressures and temperatures found tens to hundreds of miles beneath the surface, certain minerals can incorporate water molecules directly into their crystal lattices. The total amount of water stored this way in the mantle may equal or even exceed the water in all of Earth's oceans. This mantle water plays a crucial role in plate tectonics, making rocks more pliable and affecting how they flow and deform over geological time. When mantle rocks rise and experience lower pressures, such as at mid-ocean ridges where new oceanic crust forms, they release this water, which can then make its way to the surface through volcanic activity. Volcanoes, in fact, are one way Earth recycles water between its surface and its interior. Water carried down into the mantle by subducting tectonic plates can be released back to the surface through volcanic eruptions, sometimes after spending millions of years in the deep Earth. The steam you see rising from a volcanic vent might contain water molecules that began their journey at the ocean surface, were carried down as part of a subducting plate, spent eons in the hot mantle, and are now returning to the surface to begin the cycle again. The hidden layer. As we continue our gentle exploration, let us turn our attention to something that exists in almost complete darkness, yet plays a vital role in how our planet works. A hidden layer of life in the ocean that was only recently discovered to exist on the scale that it does. In the ocean depths, generally between about 600 and 3,000 feet below the surface, there exists a layer that appears on sonar as if it were the sea floor itself. Early oceanographers called it the deep scattering layer because it reflects sound waves so effectively. For years, scientists were puzzled by this mysterious layer that seemed to rise toward the surface at night and sink during the day. The mystery was solved when researchers realized that this phantom bottom was actually composed of countless trillions of small fish, squid, jellyfish, and other organisms engaged in the largest migration on Earth. A vertical journey of thousands of feet performed every single night. This daily migration is driven by a simple survival strategy. During daylight hours, these organisms remain in the dim depths where they're harder for predators to see. When darkness falls and the surface waters become safer, they swim upward to feed on the abundant plankton near the surface. Before dawn, they retreat back to the depths. This mass movement of biomass transfers enormous amounts of energy and nutrients from the surface to the deep ocean, playing a crucial role in the ocean's biological pump, the process by which the ocean absorbs and stores carbon dioxide from the atmosphere. The scale of this migration is staggering. The total weight of organisms involved may exceed 1 billion tons, making it the largest movement of animals on Earth. This includes billions upon billions of small lanternfish, creatures generally only a few inches long that possess light-producing organs on their bodies. These bioluminescent organs help the fish communicate with each other, attract prey, confuse predators, and even camouflage themselves by producing light that matches the faint glow filtering down from the surface, a technique called counter-illumination that makes them nearly invisible when viewed from below. The deep scattering layer also includes many species that humans rarely see and didn't even know existed until recently. New species are discovered regularly in these depths. Some of these organisms have remarkable adaptations to the pressure and darkness of the deep sea. Many have enormous eyes to capture every photon of light in the dim depths. Others have no eyes at all, relying instead on other senses to navigate and find food. Many produce their own light through bioluminescence, creating a twilight world of blue and green glows in the darkness. This hidden layer of life affects Earth's climate in ways that scientists are only beginning to understand. When these organisms feed near the surface and then return to the depths to digest their food and excrete waste, they're effectively transporting carbon from the surface to the deep ocean. Some of this carbon sinks further still, eventually reaching the seafloor, where it can be locked away in sediments for thousands or millions of years. This biological pump is one of the mechanisms by which the ocean absorbs carbon dioxide from the atmosphere, helping to regulate Earth's climate over long timescales. The deep ocean itself holds mysteries that we're only beginning to explore. More than 80% of the ocean has never been mapped, observed, or explored by humans. We know more about the surface of the Moon or even Mars than we know about the deepest parts of our own ocean. The ocean floor contains mountain ranges taller than the Himalayas, canyons deeper than the Grand Canyon, vast abyssal plains that stretch for thousands of miles, and strange ecosystems that exist in complete darkness, powered not by sunlight but by chemical energy seeping from Earth's interior. At hydrothermal vents, where seawater seeps into cracks in the ocean floor, gets heated by magma below, and then erupts back into the ocean at temperatures exceeding 700 degrees Fahrenheit, entire ecosystems thrive in conditions that would seem utterly hostile to life. Giant tube worms, some reaching lengths of 8 feet or more, live clustered around these vents, surviving not on food they eat, but on organic compounds produced by bacteria living within their tissues. These bacteria use the chemical energy from the vent fluids to power their metabolism, essentially substituting chemical energy for sunlight. This discovery revolutionized our understanding of life's requirements and suggested that life might exist in places previously thought to be completely barren. The ocean depths also preserve a record of Earth's history in their sediments. As particles slowly settle through miles of water and accumulate on the seafloor, they create layers that record environmental conditions through time. These sediments contain the shells of microscopic organisms that lived in the surface waters, volcanic ash from eruptions, dust blown from continents, and even micrometeorites from space. By drilling cores from the deep seafloor and analyzing their layers, scientists can reconstruct past climates, track the movements of continents, and understand how ocean chemistry has changed over millions of years. The electric planet now. Let us rise from the ocean depths to explore something that surrounds us constantly, yet remains invisible to our senses: the electrical nature of Earth itself and the extraordinary electromagnetic phenomena that occur in the atmosphere above our heads. Earth is essentially a giant battery, maintaining a constant electrical field between the surface and the upper atmosphere. In fair weather, this field has a strength of about 100 volts per meter, meaning that your head is literally at a higher voltage than your feet. You don't notice this because air is normally an excellent insulator, preventing current from flowing. However, this electrical field is constantly maintained by thunderstorms occurring around the planet. At any given moment, approximately 2,000 thunderstorms are active somewhere on Earth, generating lightning strikes roughly 100 times per second worldwide. Each lightning bolt is a massive electrical discharge, temporarily equalizing the voltage difference between clouds and ground. These bolts can reach temperatures 5 times hotter than the surface of the sun in a channel only a few inches wide, heating the air so rapidly that it explodes outward as thunder. The total energy in a single lightning bolt could power an average home for several weeks, yet this energy is released in a fraction of a second. The rapid heating and cooling of air by lightning also produces nitrogen oxides, which can be absorbed by rain and delivered to the soil as natural fertilizer. It's estimated that lightning produces millions of tons of nitrogen compounds each year, contributing significantly to the nitrogen available for plant growth. But lightning is just the most obvious manifestation of atmospheric electricity. Above thunderstorms, in the thin upper atmosphere, strange electrical phenomena occur that weren't even photographed until the 1990s because they happen so quickly and are visible only from above the storms themselves. These phenomena have been given whimsical names: sprites, elves, and blue jets. Sprites are enormous electrical discharges that extend upward from the tops of thunderstorms, reaching heights of 50 miles or more. They glow red and white and exist for only a few milliseconds, appearing as ghostly jellyfish shapes in the upper atmosphere. Elves are expanding rings of light that appear at the base of the ionosphere, growing to hundreds of miles in diameter in less than 1,000th of a second. Blue jets shoot upward from thunderstorm tops at speeds exceeding 60 miles per second, extending as high as 30 miles before fading away. These phenomena occur in the mesosphere and lower ionosphere, regions of the atmosphere so high that conventional aircraft cannot reach them and where the air is far too thin to breathe. Yet even at these altitudes, electrical processes are constantly at work. The ionosphere itself, extending from about 30 to 600 miles altitude, is a layer of the atmosphere where solar radiation is strong enough to strip electrons from atoms, creating a soup of electrically charged particles. This layer plays a crucial role in radio communication, as radio waves can bounce off the ionosphere and travel far beyond the horizon. The ionosphere's properties change with the time of day, the season, solar activity, and other factors, which is why AM radio stations can often be heard hundreds of miles away at night, but only locally during the day. Earth's magnetic field, generated by the movement of molten iron in the planet's outer core, extends far into space, creating a protective bubble called the magnetosphere that shields us from the solar wind, a constant stream of charged particles flowing from the sun. When these solar particles interact with Earth's magnetic field and atmosphere, they create the aurora borealis and aurora australis, the northern and southern lights. These shimmering curtains of light occur when charged particles from the sun are channeled by Earth's magnetic field toward the polar regions, where they collide with atmospheric gases and cause them to glow. Oxygen atoms produce green and red light, while nitrogen produces blue and purple. The lights dance and shift because the flow of particles from the sun is constantly changing, buffeted by fluctuations in the solar wind. During particularly strong solar storms, the aurora can be seen far from the poles, sometimes as far south as the equator. Historical records describe auroral displays visible in the Caribbean and other tropical regions during extreme solar events. The most powerful solar storm in recorded history, the Carrington event of 1859, produced auroras visible worldwide and induced electrical currents strong enough to shock telegraph operators and set their equipment on fire. If a similar event occurred today, it could cause trillions of dollars in damage to electrical grids, satellites, and other infrastructure. The magnetosphere itself is not static, but constantly changing shape in response to the solar wind. On the side facing the sun, the solar wind compresses the magnetosphere to within a few thousand miles of Earth's surface. On the night side, the magnetosphere stretches out into a long tail extending hundreds of thousands of miles into space, well beyond the moon's orbit. Within this magnetotail, magnetic field lines can suddenly snap and reconnect, releasing enormous amounts of energy in what are called substorms. These substorms inject charged particles into the inner magnetosphere, creating temporary radiation belts and producing beautiful auroral displays. Earth's magnetic field does something else remarkable. It reverses periodically. Over the past 20 million years, the field has reversed about every 200,000 to 300,000 years on average, though the timing is quite irregular. During a reversal, which takes several thousand years to complete, the magnetic field becomes weaker and more complex, with multiple north and south poles appearing temporarily. The last reversal occurred about 780,000 years ago, which means we're arguably overdue for the next one, though predicting when it will happen is currently impossible. The record of these reversals is preserved in rocks, particularly in volcanic rocks that contain iron-bearing minerals. When lava cools and solidifies, these minerals align with Earth's magnetic field at that time, creating a permanent record of the field's direction. By studying the magnetic properties of rocks of different ages, scientists have reconstructed the history of geomagnetic reversals going back hundreds of millions of years. This record shows that reversals happen somewhat randomly, sometimes only a few tens of thousands of years apart, sometimes millions of years apart. The longest period without a reversal in the past 160 million years lasted some 40 million years during the Cretaceous period, when dinosaurs roamed the Earth under a magnetic field that maintained the same polarity for longer than the time from the dinosaurs' extinction to the present day. The living rock. Let us now journey deep into the Earth, below the soil and sediment, into the solid rock itself, where another unexpected realm of life exists, one that challenges our assumptions about where life can survive and how much life Earth actually hosts. Miles beneath your feet, In cracks and pores in solid rock, bacteria and archaea live in conditions that seem incompatible with life. The temperatures at these depths can exceed the boiling point of water. The pressures are enormous. There is no light, no oxygen, and no obvious source of food. Yet life persists, eking out an existence by drawing energy from chemical reactions between water and rock, or by consuming organic compounds that seep down from the surface, or even by using the slight amounts of radioactive decay heat and the chemicals that radioactive decay produces. This deep biosphere, as it's called, may contain more living biomass than all the life on Earth's surface combined. Some estimates suggest that the total mass of microorganisms living beneath the seafloor and beneath continents could approach or exceed the mass of all plants, animals, fungi, and surface microbes put together. These deep organisms live life in extreme slow motion. In the cold, deep rocks, where temperatures are low enough and nutrients scarce enough, some microbes may divide only once per 1,000 years, or even once per 10,000 years. They exist in a state that barely qualifies as living by surface standards, yet they persist, maintaining their genetic integrity across time spans that dwarf human civilization. These organisms have been isolated from the surface world for millions, or even hundreds of millions of years in some cases. Water trapped in rock formations when those rocks formed can still contain viable microorganisms, preserved like biological time capsules. Some of the deepest life yet found exists more than 3 miles below the seafloor, in rocks where the temperature exceeds 250 degrees Fahrenheit. At these temperatures, most proteins would denature and DNA would degrade, yet some organisms have evolved heat shock proteins and DNA repair mechanisms so efficient that they can survive and even thrive in this hellish environment. The discovery of the deep biosphere has profound implications for our understanding of how much life Earth can support and where life might exist elsewhere in the universe. If life can persist deep underground, independent of sunlight and surface conditions, then it might also exist deep beneath the surfaces of other worlds. Mars, for example, might have a deep biosphere even if its surface is sterile. The icy moons of Jupiter and Saturn, with their suspected subsurface oceans, might host entire ecosystems independent of their parent planet's sun. The deep organisms also teach us about the limits of life. Some can survive doses of radiation that would be instantly lethal to any surface organism, doses thousands of times higher than what would kill a human. Others can survive total desiccation, losing almost all their water and entering a state of suspended animation for years before reviving when water becomes available again. Some can survive pressures that would crush steel, temperatures that would melt lead, or pH levels so acidic or alkaline that they would dissolve most organic materials. Studying these extremophils, as they're called, has led to practical applications. Enzymes from heat-loving bacteria are now used in PCR, the polymerase chain reaction that allows tiny amounts of DNA to be copied millions of times for analysis. This technique, fundamental to modern biology and medicine, wouldn't be possible without heat-stable enzymes borrowed from microorganisms that live in hot springs and hydrothermal vents. Other extremophile enzymes are being developed for industrial processes, for bioremediation of contaminated sites, and for producing biofuels. The deep biosphere also plays a role in global chemical cycles. These organisms affect the chemistry of groundwater, the formation and dissolution of minerals, and even the long-term cycling of carbon between rocks and the atmosphere. When organic carbon gets buried in sediments and eventually becomes part of deep rock formations, it can be consumed by deep microbes that release methane or other gases. Some of this methane eventually makes its way back to the surface, contributing to natural gas deposits or seeping into the ocean or atmosphere. The deep organisms are thus part of the global carbon cycle, participating in the long-term regulation of Earth's climate, even though they live in perpetual darkness miles beneath the surface. The study of deep life is still in its infancy. Every time scientists drill into rocks that were previously thought to be sterile, they find life. Every time the temperature limits or pressure limits or chemical limits for life are thought to be established, organisms are discovered pushing those limits further. We're still discovering the extent of the deep biosphere, still cataloging its diversity, still trying to understand how these organisms survive and what role they play in Earth's larger systems. It's entirely possible that we share our planet with more microbial life than we ever imagined, most of it living in the dark depths of the solid Earth itself. The wandering poles. As you continue to relax and drift through these stories, let us consider something both ancient and ongoing, something that affects every compass on Earth, yet happens so slowly that no human lifetime can witness its full extent: the wandering of Earth's magnetic poles. The magnetic North Pole, the point that compasses point toward, is not fixed but moves constantly. Right now, it's moving at an accelerating rate, traveling from the Canadian Arctic towards Siberia at a speed of about 30 to 40 miles per year. This movement is faster than at any time in the past century. If the pole continues on its current trajectory, it will pass the geographic North Pole within a few decades and eventually settle somewhere in northern Russia, though predicting its exact path is difficult because the movement is driven by complex changes in the flow of molten iron in Earth's outer core, thousands of miles beneath the surface. The magnetic South Pole wanders too, though currently at a slower rate than its northern counterpart. The two poles don't move in lockstep. Each follows its own independent path determined by local variations in the magnetic field. The magnetic poles are also not directly opposite each other through Earth's center. If you stood at the magnetic North Pole and drilled straight through the planet, you would not emerge at the magnetic South Pole but at a point hundreds of miles away from it. This wandering creates practical problems. Navigation systems that rely on magnetic compasses must be regularly updated to account for magnetic declination, the angle between true north and magnetic north at any given location. Aircraft, ships, and even smartphones use models of Earth's magnetic field that must be updated every few years as the field changes. Airports must regularly renumber their runways, which are designated by the magnetic heading needed to land on them. When the magnetic field changes enough, what was runway 19 pointing to 190 degrees magnetic might need to be renamed runway 20 to reflect the new magnetic heading of 200 degrees. The magnetic field itself is generated by the geodynamo, the motion of electrically conducting molten iron in Earth's outer core. This outer core, about 1,400 miles thick, sits beneath the solid rock mantle and surrounds the solid iron inner core. The outer core is kept liquid by the intense heat from the inner core and from radioactive decay in the deep Earth. Convection currents in this liquid metal, combined with Earth's rotation, create swirling motions that generate electrical currents, which in turn produce magnetic fields. These magnetic fields interact with the flow of liquid metal, creating a self-sustaining dynamo that has operated for billions of years. The behavior of this geodynamo is chaotic in the mathematical sense, meaning that small changes in conditions can produce large changes in outcome, making long-term prediction essentially impossible. This is why we cannot predict when the next magnetic reversal will occur, or where the magnetic poles will wander in the distant future. We can only observe the current state and make short-term projections. The magnetic field does more than guide compasses. It shields Earth's surface from harmful radiation from space. The solar wind, a stream of charged particles constantly flowing from the sun, would strip away our atmosphere over time if not for the magnetic field deflecting these particles around Earth. Mars, which lost its global magnetic field billions of years ago, has had much of its atmosphere stripped away by the solar wind over geological time. Earth's magnetic field thus makes our planet more habitable, protecting the atmosphere and reducing the amount of harmful radiation reaching the surface. The strength of the magnetic field has decreased by about 10% over the past century and a half, since measurements began. Some scientists interpret this as a possible sign that a magnetic reversal might be approaching, though the field strength can also fluctuate naturally without leading to a reversal. During a reversal, which takes thousands of years to complete, the field becomes much weaker and more complex, potentially allowing more cosmic radiation to reach Earth's surface and disrupting navigation systems and potentially even technological infrastructure. Despite these changes, life has survived countless magnetic reversals over Earth's history. The last reversal, 780,000 years ago, occurred during a time when early humans were already present. While increased radiation during reversals might affect some organisms, particularly those living at high altitudes or in polar regions, there's no evidence that reversals cause mass extinctions. Life is resilient, and the temporary increase in radiation during a reversal is small compared to other environmental challenges that species have survived. The magnetic field also creates beautiful visual phenomena beyond the aurora. The Van Allen radiation belts, regions of space where charged particles from the solar wind are trapped by Earth's magnetic field, glow faintly in ultraviolet light. These belts form two donut-shaped regions around Earth, extending from a few hundred to tens of thousands of miles above the surface. Satellites passing through these belts must be shielded against the intense radiation, which can damage electronics and solar panels. The mountain that walks now. Let us turn our attention to a different kind of motion, one that occurs on a different timescale but with consequences that shape continents and reshape the face of our planet. The slow but inexorable movement of Earth's tectonic plates. The solid ground beneath your feet is moving. The tectonic plate you're standing on is drifting across Earth's surface at roughly the same rate your fingernails grow, typically a few inches per year. This might seem imperceptibly slow, but over millions of years, these tiny movements add up to journeys of thousands of miles. The rock beneath your feet has traveled across Earth's surface, possibly crossing oceans, possibly migrating from different climatic zones, carrying the record of its journey in its minerals and fossils. The Atlantic Ocean is getting wider by about an inch per year as new oceanic crust forms at the mid-Atlantic ridge and pushes North America and Europe farther apart. Meanwhile, the Pacific Ocean is shrinking as its edges are consumed in subduction zones where oceanic plates slide beneath continental plates. In a few 100 million years, the Pacific might close entirely, and the continents might reunite into a new supercontinent, just as they did in the past to form Pangaea. This motion is driven by convection in Earth's mantle, the thick layer of hot rock between the crust and the core. Although the mantle is solid, it flows slowly over geological time, like very thick honey or putty. Hot material rises from deep in the mantle, cools as it approaches the surface, and then sinks back down, creating massive circulation patterns that drag the tectonic plates along. This process has been operating for billions of years and will continue for billions more until Earth's interior cools enough that convection stops, though that won't happen for eons to come. Where plates collide, mountains rise. The Himalayas are still growing taller as the Indian plate continues to push into the Eurasian plate, the same collision that began around 50 million years ago. Mount Everest itself gains a few millimeters of height each year, though erosion from wind, water, and ice constantly works to wear it down. The competition between uplift and erosion determines the ultimate height of mountains, and the Himalayas are currently winning this competition, remaining the tallest mountain range on Earth. Where plates pull apart, rift valleys form and eventually new ocean basins. The East African Rift is a place where a continent is actively splitting apart. In a few million years, the eastern part of Africa may separate entirely from the rest of the continent, forming a new ocean basin. We can see earlier stages of this process frozen in the geological record of other continents, showing that what's happening in East Africa today has happened many times in Earth's past. The boundaries between plates are where most earthquakes and volcanic eruptions occur. The Ring of Fire encircling the Pacific Ocean is a region of intense seismic and volcanic activity where oceanic plates subduct beneath continental plates or other oceanic plates. The friction of these grinding plates releases enormous energy in the form of earthquakes, and the melting of the subducted plate produces magma that rises to feed volcanoes. Some 3/4 of Earth's active volcanoes are found in this ring. Subduction zones are also sites of remarkable geological recycling. As an oceanic plate descends into the mantle, it carries with it water, sediments, and even fragments of ocean crust and marine organisms. This material is carried deep into Earth's interior, where some of it melts and returns to the surface through volcanic eruptions, while some may be transported all the way to the core mantle boundary thousands of miles below. Material subducted millions or billions of years ago may still be slowly sinking through the mantle, creating a complex three-dimensional structure that geophysicists are only beginning to map using seismic waves from earthquakes. The movement of continents has profound effects on climate. When continents drift into polar regions, ice can accumulate on land, leading to ice ages. When continents cluster around the equator, there's less land for ice to accumulate on, and the climate may be warmer globally. The configuration of continents also affects ocean circulation patterns. When a supercontinent exists, ocean currents can flow around the whole world at the equator, creating different heat distribution than when continents are dispersed and ocean currents must navigate between them. The collision and separation of continents also affects biological evolution. When continents join, organisms that evolved in isolation can suddenly come into contact, sometimes with dramatic results as new predators or competitors arrive. When continents separate, populations are split and may evolve in different directions, increasing biodiversity. The current distribution of life on Earth reflects the breakup of Pangaea and the subsequent drift of continents to their current positions. Fossils of identical species on continents now separated by thousands of miles of ocean provide some of the strongest evidence for continental drift. The invisible river in the sky. Let us now rise from the solid Earth to explore something that flows overhead in the atmosphere, unseen yet carrying more water than the greatest rivers on Earth's surface. The atmospheric rivers that transport moisture from the tropics to higher latitudes. High in the atmosphere, narrow corridors of concentrated moisture flow like rivers in the sky. These atmospheric rivers can be thousands of miles long but only a few hundred miles wide, and they transport enormous quantities of water vapor. A single atmospheric river can carry more water than the Mississippi River, though in vapor form rather than liquid. When these rivers encounter mountains or other conditions that force the air to rise and cool, the moisture condenses and falls as rain or snow, sometimes at extraordinary rates. The west coast of North America experiences atmospheric rivers regularly, particularly in winter. When one makes landfall in California or the Pacific Northwest, it can dump several inches of rain in just a few days, sometimes causing flooding, but also providing much of the region's water supply. In California, atmospheric rivers deliver 30 to 50% of the state's annual precipitation, despite being present only a few days per year. They fill reservoirs, replenish groundwater, and feed the snowpack in the Sierra Nevada mountains that provides water for agriculture and cities throughout the dry summer months. These atmospheric rivers originate in the tropics, where warm ocean waters evaporate into the air, creating moisture-rich air masses. Trade winds and other atmospheric circulation patterns organize this moisture into narrow corridors that flow toward higher latitudes. The Pineapple Express, a well-known atmospheric river that affects the western United States, gets its name because it often originates near Hawaii, pulling tropical moisture northeastward toward North America. While atmospheric rivers are a crucial source of water, they can also cause disasters. When a strong atmospheric river stalls over a region, it can produce flooding rainfall that overwhelms rivers and causes landslides. The combination of heavy rain falling on saturated soil, especially in mountainous terrain, can trigger debris flows that sweep away everything in their path. Climate change is expected to intensify atmospheric rivers, making the heaviest precipitation events even more extreme, though the total number of atmospheric rivers might not change much. Similar phenomena occur in other parts of the world. The South American monsoon is partially driven by atmospheric rivers bringing moisture from the Atlantic Ocean deep into the Amazon basin. The Asian monsoon systems also involve atmospheric rivers transporting moisture from tropical oceans onto the continents. Understanding these atmospheric rivers is crucial for water resource management and flood prediction, yet they were only identified and named in the 1990s. Despite carrying such enormous quantities of water and having such significant impacts, they remained essentially unknown to science until recently. The water vapor in these atmospheric rivers originates from evaporation over the oceans, particularly in the tropics, where warm water and strong solar heating create high evaporation rates. This water vapor is actually the atmosphere's largest source of stored energy. When vapor condenses back into liquid, it releases latent heat, the energy that was required to evaporate the water in the first place. This energy release drives atmospheric circulation, powers storms, and transports heat from warm regions to cool regions. The atmosphere is essentially a heat engine, and water vapor is its working fluid. Clouds within atmospheric rivers can have complex vertical structures. At lower altitudes, clouds might consist of liquid water droplets, while at higher, colder altitudes they contain ice crystals. The transition zone where ice and liquid coexist is particularly important for precipitation formation. Ice crystals can grow rapidly in this zone by capturing water vapor and by colliding with and capturing liquid droplets, a process called rimming. These growing crystals eventually become heavy enough to fall, forming snow that may melt into rain as it descends through warmer air. The precipitation from atmospheric rivers can be enhanced when the moist air encounters mountains. As air is forced to rise over the mountains, it expands and cools, causing water vapor to condense. This orographic precipitation creates a rain shadow effect, wet windward slopes and dry leeward slopes. The wettest places on Earth, like Cherrapunji in India, or the western slopes of the Pacific Northwest Mountains, owe their extreme rainfall to this mechanism, with atmospheric rivers providing the moisture and mountains forcing it to fall as rain. The ancient light. As we drift deeper into these stories, allowing them to ease you toward rest, consider something both immediate and ancient. The light that surrounds you right now, illuminating your world and making vision possible, has a history stretching back to the birth of the universe itself. The sunlight that warms Earth's surface began its journey in the core of the sun, where nuclear fusion converts hydrogen into helium under temperatures and pressures so extreme that they exceed our earthly experience. In the sun's core, photons, particles of light, are created through fusion reactions. But these newborn photons cannot travel directly to Earth. Instead, they must make a long, difficult journey through the sun itself. The sun is so dense that photons can only travel a tiny fraction of an inch before being absorbed by an atom and then re-emitted in a random direction. This random walk through the sun's interior takes an extraordinarily long time. A photon might take anywhere from 100,000 to 1,000,000 years to journey from the core to the sun's surface, bouncing and zigzagging through the dense solar plasma in a drunkard's walk that eventually, by chance, carries it outward. Once it reaches the surface, that photon then travels through space at light speed, covering the 93 million miles to Earth in about 8 minutes. This means the sunlight you see right now, the light illuminating your skin and the world around you, was created in the sun's core sometime between the dawn of agriculture and the present day. The photons warming you might have been created when your ancestors were hunter-gatherers, or when the first cities were being built, or during the age of the dinosaurs if that photon had a particularly long journey through the sun's interior. The light you see is ancient, yet it seems fresh and immediate. When sunlight enters Earth's atmosphere, it encounters air molecules, dust particles, and water droplets that scatter the light in all directions. This scattering is why the sky appears blue. Shorter wavelengths of light, which we perceive as blue, scatter more efficiently than longer wavelengths. The sun itself appears yellow or white from Earth's surface because we're seeing the colors that weren't scattered away. At sunset, when sunlight must travel through more atmosphere to reach your eyes, even more of the shorter wavelengths are scattered out, leaving the longer red and orange wavelengths to dominate, painting the sky in brilliant colors. The light from the sun drives almost all life on Earth through photosynthesis. Plants, algae, and some bacteria capture photons and use their energy to convert carbon dioxide and water into sugars and oxygen. This process is the foundation of nearly every food chain on the planet. The food you eat, whether plant or animal, contains energy that ultimately came from sunlight captured by photosynthesis. When you move your muscles, think with your brain, or maintain your body temperature, you're using energy that was sunlight sometimes months or years ago, captured by a plant, perhaps eaten by an animal, and eventually consumed by you. But sunlight is not the only ancient light around you. If you look up at the night sky, you're seeing light from stars that may have traveled for years, centuries, or even millions of years to reach your eyes. The nearest star beyond our sun, Proxima Centauri, is about 4 light-years away, meaning the light you see from it left that star 4 years ago. Other stars visible to the naked eye may be hundreds or thousands of light-years distant. Some of the stars you see might have actually died already, but their light is still traveling through space and has not yet delivered the news of their demise to Earth. The most distant objects visible to the naked eye are even more remarkable. The Andromeda Galaxy, a faint smudge of light visible on dark nights, is about 2.5 million light-years away. The light you see from Andromeda left that galaxy when our earliest human ancestors were just beginning to walk upright in Africa. That ancient light has been traveling through the void of space ever since. And tonight, it finally arrives at your eye, completing a journey that predates human civilization, predates our species, predates most of human evolution. Light also provides a window into Earth's past through the study of rocks and minerals. Some minerals preserve evidence of ancient radiation exposure or ancient light conditions. Certain crystals can record the intensity of Earth's magnetic field at the time they formed, which is related to cosmic radiation levels. Amber, fossilized tree resin, can preserve organisms and even bubbles of ancient atmosphere, sealed away for millions of years. When scientists examine amber under microscopes and spectroscopes, they're analyzing light that has interacted with materials and organisms from Earth's distant past, reading messages encoded in wavelengths and intensities. The singing Earth. Let us now attune ourselves to something most people never hear, though it surrounds us always. The subtle vibrations and sounds produced by Earth itself, a planetary symphony playing continuously in frequencies below the threshold of human hearing. Earth hums. Seismographs placed around the world detect a constant, low-frequency vibration of the planet itself, oscillating at periods of roughly 300 seconds. Far too slow to hear directly, more than 1,000 times slower than the lowest note audible to human ears. This hum occurs even when no earthquakes are happening, even on the quietest geological days. For years after its discovery, scientists debated the source of this mysterious vibration. Recent research suggests it's caused by ocean waves interacting with the seafloor, creating pressure variations that make the entire planet ring like a slowly struck bell. The ocean waves that create this hum aren't the surface waves you see at the beach, but much more subtle pressure variations created by storm systems moving across the ocean. When waves of particular frequencies and heights interact, they can create standing waves, pressure fluctuations that don't travel across the ocean surface but instead pulse up and down in place. These standing waves push on the seafloor, and because the ocean covers about 70% of Earth's surface, this pushing creates a global pattern of pressure that makes the whole planet vibrate gently. This hum is distinct from the more dramatic seismic waves generated by earthquakes. When a major earthquake occurs, seismographs around the world detect waves that have traveled through Earth's interior. These waves come in different types: P waves, or primary waves, that compress and expand rock as they travel; S waves, or secondary waves, that shake rock from side to side; and surface waves that travel along Earth's surface rather than through its interior. By analyzing the timing and characteristics of these waves, seismologists can determine exactly where an earthquake occurred, how deep it was, and how much energy it released. The waves from the largest earthquakes can make the entire planet ring like a bell for days afterward. After an extremely large earthquake, Earth can oscillate at dozens of different frequencies simultaneously, each corresponding to a particular mode of vibration. Some of these modes make the planet alternately expand and contract, breathing in and out. Others make it twist or oscillate in more complex patterns. By studying these free oscillations, scientists have learned about Earth's internal structure, much as listening to a bell's tone can tell you about its size, shape, and composition. Volcanic eruptions also produce distinctive seismic signatures. Before an eruption, magma moving underground creates harmonic tremor, a sustained seismic signal that sounds like a musical tone when sped up to audible frequencies. Different volcanoes have characteristic tremor frequencies, like individual voices. Some volcanic events create signals that sound like drum beats, while others produce more continuous tones. Seismologists monitoring active volcanoes listen to these signals, both literally and figuratively, listening for changes that might herald an eruption. Even without earthquakes or volcanoes, Earth's crust is never truly silent. Rocks under stress make tiny creaking and popping sounds as they slowly deform. Glaciers groaning as they flow downhill create seismic signals. Avalanches, landslides, and even large storms generate vibrations that seismographs can detect. Rivers and streams create constant subtle vibrations. Trees swaying in the wind transfer some of their motion to the ground. All of these sources combine to create a complex background of seismic noise against which earthquake signals must be detected. The ocean itself sings in various ways. Besides creating Earth's hum through pressure variations on the seafloor, waves breaking on coastlines create seismic signals that can be detected far inland. The largest ocean waves, generated by powerful storms, create enough pressure variation to register on seismographs on the opposite side of the Earth. Ice shelves in Antarctica create distinctive signals when icebergs carve from them, or when meltwater drains through them. These signals can be analyzed to understand ice shelf stability and melting rates, providing information about climate change from the seismic data. Human activities also contribute to Earth's seismic background. Trains, trucks, construction equipment, industrial machinery, and even large crowds of people all create ground vibrations that seismographs detect. In cities, this anthropogenic noise can be significant enough to interfere with detecting small earthquakes. During the COVID-19 pandemic lockdowns, when human activity decreased dramatically, seismologists noted that seismic noise levels dropped substantially, making it easier to detect small earthquakes and other natural seismic signals. This unintentional experiment demonstrated just how much humans contribute to making Earth's surface vibrate. The invisible ocean. As you continue to relax into these stories, drifting peacefully, let us explore an ocean that most people never see or think about. An ocean not of water, but of air, the atmosphere that surrounds us and makes life possible. The atmosphere is essentially an ocean of gas held to Earth by gravity, gradually thinning as altitude increases until it merges imperceptibly with the vacuum of space. Unlike the ocean of water, which has a definite surface, the atmosphere has no clear upper boundary. It simply becomes progressively more tenuous until there's effectively nothing there. The conventional boundary between atmosphere and space, the Kármán line at about 62 miles altitude, is arbitrary, chosen because above this altitude, a craft must travel faster than orbital velocity to generate enough lift to stay aloft. This ocean of air weighs an enormous amount. The total mass of the atmosphere is about 5 quadrillion tons, enough to create the atmospheric pressure we experience at sea level, where the weight of all the air above you presses down with a force of about 14.5 pounds on every square inch of your body. You don't notice this because your body's internal pressure balances it. When you climb a mountain, the air pressure decreases because there's less atmosphere above you. At the summit of Mount Everest, the pressure is only about 1/3 what it is at sea level, making breathing extremely difficult without supplemental oxygen. The atmosphere consists mostly of nitrogen and oxygen, with small amounts of argon, carbon dioxide, and other gases. This composition hasn't always been the same. Earth's earliest atmosphere, outgassed from volcanoes billions of years ago, contained almost no oxygen and much more carbon dioxide. The rise of oxygen in the atmosphere, beginning about 2.5 billion years ago, was driven by cyanobacteria, photosynthetic microorganisms that produced oxygen as a waste product. This oxygen initially combined with dissolved iron in the oceans, creating enormous deposits of iron oxide that formed banded iron formations now visible in ancient rocks. Only after the ocean's iron was saturated did oxygen begin to accumulate in the atmosphere, eventually reaching levels high enough to support complex life. The atmosphere is structured in layers. The troposphere, the lowest layer where weather occurs, extends from the surface to about 6 to 12 miles altitude depending on latitude and season. Almost all of Earth's water vapor and clouds exist in this layer. Above the troposphere lies the stratosphere, extending to about 30 miles altitude. The stratosphere contains the ozone layer, where ultraviolet light from the sun breaks apart oxygen molecules and allows them to recombine into ozone, a molecule consisting of 3 oxygen atoms instead of the usual 2. This ozone absorbs most of the sun's ultraviolet radiation, protecting life on Earth's surface from this harmful energy. Without the ozone layer, life on land would be difficult or impossible, as UV radiation damages DNA and other biological molecules. Higher still lies the mesosphere, extending to about 50 miles altitude, where meteors burn up as they enter the atmosphere at high speed. The friction with air molecules, sparse as they are at this altitude, creates enough heat to vaporize most meteors before they can reach the surface. We see this vaporization as shooting stars streaking across the night sky. The largest meteors may survive passage through the atmosphere to strike the surface as meteorites, but most of the thousands of tons of cosmic material that enter Earth's atmosphere daily are vaporized in the mesosphere. Above the mesosphere is the thermosphere, where temperatures rise with altitude due to absorption of extreme ultraviolet and X-ray radiation from the sun. Despite these high temperatures, the air is so thin that you would freeze if placed there without a spacesuit. Temperature measures the average energy of individual molecules, but with so few molecules present, there's not enough total heat energy to warm a human body. This is also the altitude where the aurora occurs and where the International Space Station orbits. The outermost layer, the exosphere, extends from about 400 miles altitude to several thousand miles, gradually merging with the interplanetary medium. In this region, individual atoms and molecules can travel large distances without colliding with others. Some molecules moving fast enough can escape Earth's gravity entirely and be lost to space. Earth is constantly losing some of its atmosphere this way, though the loss rate is so slow that it won't significantly deplete the atmosphere for billions of years. The atmosphere does something remarkable. It acts as a blanket that moderates temperature extremes. Without an atmosphere, Earth's surface temperature would plunge to hundreds of degrees below freezing on the night side and soar to hundreds of degrees above freezing on the day side, much like the moon experiences. The atmosphere absorbs heat from the surface and redistributes it through convection and radiation, keeping temperatures relatively moderate. Water vapor, carbon dioxide, and other greenhouse gases play a crucial role by absorbing infrared radiation emitted by Earth's surface and re-radiating some of it back downward, warming the surface beyond what solar radiation alone would achieve. Wind, the movement of air driven by pressure differences created by uneven heating of Earth's surface, redistributes heat and moisture around the planet. The fastest winds on Earth occur in the jet streams, narrow ribbons of extremely fast-moving air in the upper troposphere, where wind speeds can exceed 200 miles per hour. These jet streams steer weather systems and affect air travel. Flights from west to east can be significantly faster than east to west because they ride the jet stream, while flights in the opposite direction must fight against it. The memory of water. Now let us consider something intimate and universal, water, and how the water molecules in your body have journeyed through Earth's systems for billions of years, passing through countless other organisms and environments before becoming part of you. The water you drink today, the water in your cells, the water in your blood, has been cycling through Earth's hydrosphere for more than 4 billion years. Those specific water molecules might have fallen as rain on ancient fern forests, might have been drunk by a dinosaur, might have flowed in rivers that no longer exist, might have been frozen in glaciers that covered continents, might have been part of the ocean when the first fish evolved. Water molecules are constantly being assembled and disassembled through chemical reactions, but the hydrogen and oxygen atoms that compose them are ancient. having been present on Earth since its formation or delivered by comets and asteroids in the early solar system. A single water molecule might spend anywhere from a few days to thousands of years in any particular reservoir. In the atmosphere, as we discussed earlier, the average residence time is about 9 days before precipitation returns that water to the surface. In rivers, water molecules might spend a few weeks before reaching the ocean. In the ocean itself, the average molecule might remain for thousands of years before evaporating back into the atmosphere. In ice sheets and glaciers, water can remain frozen for hundreds of thousands or even millions of years. In groundwater, particularly deep groundwater, residence times can exceed 10,000 years. When you drink a glass of water, you're taking in roughly 25 sextillion molecules, a number so large it's nearly incomprehensible. Given that Earth's water has been cycling for billions of years, and that water molecules are constantly moving between different reservoirs, the probability is essentially 100% that the water you just drank contains molecules that were once part of countless other organisms. Some of the water in your body was once in a cloud, was once in a river, was once drunk by ancient peoples, was once part of a woolly mammoth, was once frozen in an iceberg. Your body is about 60% water by weight, meaning a typical adult contains about 40 liters or 10 gallons of water. This water is constantly turning over. You lose water through breathing, sweating, and waste elimination, and you replace it by drinking and eating. The water in your body has an average residence time of about 9 to 16 days, though different body compartments turn over at different rates. The water in your blood might be replaced in just a few hours, while water in bone or fat tissue might remain for weeks or months. Water is essential to life as we know it because of its unique properties. It's one of the few common substances that exists naturally in all three states, solid, liquid, and gas, within Earth's temperature range. It has an unusually high heat capacity, meaning it can absorb or release large amounts of heat without changing temperature much, which helps regulate body temperature and moderate Earth's climate. It's an excellent solvent, dissolving more substances than any other common liquid, which is why blood, sap, and cellular fluids are all water-based. They can transport nutrients, wastes, and chemical signals dissolved in the water. Water also has the unusual property of being less dense as a solid than as a liquid, which is why ice floats. This seemingly simple fact has profound consequences. If ice sank, lakes and oceans would freeze from the bottom up, potentially freezing completely in winter and killing all aquatic life. Because ice floats, it forms an insulating layer on top that keeps the water below from freezing, allowing life to persist through winter. This property has been crucial for the evolution and persistence of life on Earth. The cycling of water through different states and reservoirs drives many of Earth's processes. The water cycle transports heat from the tropics toward the poles as water vapor evaporates in warm regions, is carried poleward by atmospheric circulation, and releases its heat when it condenses and precipitates in cooler regions. This heat transport moderates global temperature differences. The water cycle also drives erosion, transporting dissolved and suspended materials from the continents to the oceans, gradually wearing down mountains and reshaping landscapes. Plants are intimately involved in the water cycle through transpiration, the evaporation of water from their leaves. A large tree can transpire hundreds of gallons of water per day, drawing it up from the soil through their roots and vascular systems, and releasing it through tiny pores in their leaves. This transpired water vapor enters the atmosphere and can precipitate elsewhere, effectively recycling water through the biosphere. In the Amazon rainforest, so much water is transpired by the trees that much of the rain falling in the western Amazon is actually water that was previously transpired by trees in the eastern Amazon, cycled through the atmosphere multiple times before finally flowing out in rivers to the ocean. The patient stones. As we near the end of our journey together, let us consider the very foundation beneath everything, the rocks that form Earth's crust, some of which have witnessed nearly the entire history of our planet, silently recording in their structure the events of billions of years. The oldest rocks on Earth's surface are more than 4 billion years old, formed when Earth itself was only about 500 million years old. These ancient rocks have survived countless cycles of mountain building and erosion, continental collision and separation, climate changes from hothouse to icehouse and back again. They're found in only a few places: the Canadian Shield, Western Australia, Greenland, and parts of Africa, where ancient continental crust has somehow escaped being recycled back into the mantle through subduction or being destroyed by erosion. These rocks tell stories of an early Earth that was alien compared to today. Some ancient rocks show evidence of being formed in water, suggesting that oceans existed as early as 4 billion years ago. Others contain minerals that could only have formed in oxygen-poor conditions, confirming that Earth's early atmosphere contained little or no oxygen. Some preserve chemical signatures that might indicate the presence of early life, though interpreting such ancient evidence is extremely difficult and controversial. Rocks form through three main processes, creating the three major rock types. Igneous rocks crystallize from molten magma or lava. When magma cools slowly underground, large crystals have time to grow, forming rocks like granite, with visible mineral crystals. When lava erupts at the surface and cools rapidly, crystals remain microscopic, forming rocks like basalt with a fine-grained texture. Sedimentary rocks form from accumulated sediment, sand, mud, shells, or other materials that are buried, compacted, and cemented together. These rocks often contain fossils and preserve detailed records of ancient environments. Metamorphic rocks form when existing rocks are subjected to heat and pressure, sufficient to change their mineral composition or structure without melting them completely. Marble forms from limestone, schist from shale, all transformed by heat and pressure deep in Earth's crust. Each rock type records information about its formation conditions. The minerals in an igneous rock tell us about the temperature and composition of the magma it formed from. The texture tells us how fast it cooled. Chemical analysis can reveal where the magma came from and what processes it underwent before solidifying. Sedimentary rocks preserve even more information. The grain size tells us about the energy of the environment where they formed, with fine mud settling in calm water and coarse sand or gravel requiring faster currents. The structures in sedimentary rocks, ripple marks, mud cracks, raindrop impressions, even fossil footprints, preserve snapshots of ancient moments. Fossils in sedimentary rocks provide our only direct evidence of life's history on Earth. The oldest suspected fossils are more than 3.5 billion years old, though these are so ancient and altered that not all scientists agree they're truly biological in origin. Clear fossils of cells and microbial mats appear in rocks around 3 billion years old. The first large, complex organisms appear in the fossil record around 600 million years ago, and from that point forward, the fossil record becomes increasingly detailed, documenting the evolution of life from simple animals to fish, to amphibians, to reptiles to mammals, from marine organisms to creatures that colonized land. Reading the rock record requires piecing together clues like a detective solving an ancient mystery. A layer of volcanic ash between sedimentary rocks marks a moment when a volcano erupted, burying everything beneath ash. The ash can be dated radiometrically, providing an exact age for that layer and constraining the ages of fossils found above and below it. A layer of limestone indicates a time when a warm, shallow sea existed, while sandstone might indicate a beach or desert. Coal seams mark ancient swamps where vegetation accumulated faster than it could decay. Each rock layer is a page in Earth's autobiography, and learning to read the rocks allows us to reconstruct vanished worlds. Some rocks preserve evidence of catastrophic events. The boundary between the Cretaceous and Paleogene periods, marking the extinction of the dinosaurs 66 million years ago, is visible in many places as a thin layer of clay enriched in iridium, an element rare on Earth's surface but common in asteroids. This layer is debris from the asteroid impact that caused the extinction, spread globally by the atmosphere and then settled to the seafloor. Below this layer, rocks contain dinosaur fossils. Above it, they don't. The rocks record one of life's greatest catastrophes with remarkable clarity. The slowest geological processes produce the most dramatic results. Mountain ranges rise at rates of millimeters per year. Yet given millions of years, this imperceptible motion can elevate rocks from the seafloor to heights of 5 miles or more. The Himalayas contain marine fossils near their summits, limestone that formed in a shallow tropical sea that existed where India and Asia now collide. These rocks were horizontal sediments on a seafloor, then were compressed, folded, and uplifted as the continental collision proceeded, eventually becoming the highest peaks on Earth. The rocks remember their origin, even in their transformed state. Erosion works as slowly as mountain building, wearing away mountains grain by grain. Yet given enough time, erosion can reduce mighty mountain ranges to gentle hills. The Appalachian Mountains, which once rivaled the Himalayas in height when they formed around 300 million years ago, have been worn down by erosion to a fraction of their former grandeur. The sediments eroded from ancient mountains are deposited elsewhere, forming new sedimentary rocks that preserve clues about the mountains that produced them. Thus the rock cycle continues: creation and destruction, formation and erosion, an endless recycling of Earth's crust operating on timescales that dwarf human civilization. Conclusion. The story continues. As our journey through Earth's hidden stories comes to a gentle close, remember that these facts are not just interesting trivia, but windows into understanding our place in a vast, ancient, and dynamic system. The planet beneath you is not a static stage for human activity, but an active participant in an ongoing story billions of years old. Every breath you take connects you to the living world through the oxygen produced by photosynthesis. Every glass of water you drink connects you to the water cycle that has operated for billions of years. Every step you take is on rocks that remember their own long histories. You exist within nested systems, your body within ecosystems, ecosystems within climate zones within a planet, the planet within a solar system, the solar system within a galaxy, the galaxy within a universe. Earth has been here long before humans and will continue long after we're gone, patiently cycling its materials, breathing with the seasons, drifting through space on its journey around the sun. The underground lakes, the breathing forests, the wandering magnetic poles, the singing rocks, the ancient water. All these phenomena continue right now while you rest, operating according to physical and biological laws that care nothing for human awareness, yet create the conditions that make our existence possible. Let these stories remind you of the profound mystery and beauty of the natural world. Let them inspire curiosity about the countless other secrets Earth still holds, and let them ease you into peaceful sleep, knowing that you're part of something much larger and older than yourself, a brief participant in Earth's grand ongoing story, sheltered by atmosphere and magnetic field, warmed by ancient starlight, surrounded by the patient processes that have shaped and continue to shape our remarkable planet. Rest well, knowing that while you sleep, Earth continues its work, grinding continents, circulating oceans, cycling water, growing mountains, feeding ecosystems. Tomorrow when you wake, the planet will have completed another rotation, traveled another 2 million kilometers in its orbit around the sun, and continued the ancient rhythms that have sustained life for billions of years. Sleep peacefully in this knowledge, this connection, this belonging to a living world.